Yeah.
All right, we are going to, we got late start tomorrow and Wednesday. Do you guys have tests?
Next week, I think.
Next week's algebra.
Yeah.
We only have algebra.
That's it?
Yeah.
We're not.
So quiz
Yeah.
Thursday.
Use that monkey brain if you would.
Yes.
We're gonna take a thing Tuesday and Wednesday, and you're gonna sing on Voice Thursday.
You can say go, banana.
Is it Thursday this week?
Thursday this
Oh.
Hey, all right, settle down. All right, like I said, this is kind of the last main topic that we hit that's before the OST. And now this is hit pretty heavy on the OST as well. Like I said, what we've done we did 4-6, which is arithmetic sequences, but it kind of rolls into 11, 1, 2, and 3. Actually, that should be for you guys over here. Sorry.
But it's Thursday.
Thursday, we're gonna have a quiz. Like I said, with finals and everything and OST tests, we don't usually get as many summative grades as normal, so you gotta take advantage of them, especially if you're somebody that's on the borderline right now. So we don't have quite as many, so don't wait till the end to try and pick everything up. All right, we're gonna talk about exponential growth and exponential decay, which is some of the things that happen naturally that you don't even realize. Like populations can either grow exponentially or they'll decay exponentially. A lot of times investments, you want them to grow exponentially. Like if something grows 4% a year, that's going to end up being an exponential growth type of problem. If something grows 2% a year, it'll be an exponential growth problem. Things decay, medicines decay. When you take an aspirin, you take 500 milligrams. Well, it decays in your body eventually until it's down to 0, but it doesn't go from 500 to 0 in 10 minutes. It decays exponentially as it works through your bloodstream. That's another example of something that decays. All right, exponential growth occurs when a quantity increases by the same rate over the same period. It doesn't have to be years, it could be a month. So population could increase monthly by 1%. Money could grow monthly by 2%. When this happens, the value of the quantity at any given time can be calculated as a function of the rate and the original amount. Here is the equation. Now, the one thing on this OST is they give you some equations, they don't give you some from this section. That's why we got to go over them. So basically, this is the equation. Y equals A times 1 plus R to the T power. And it's important to be able to use your calculator here. A is your original amount, it's whatever you start with. R is the rate of growth as a decimal. All right, that's probably going to be the biggest issue. So here's the issue. 3%, if something is growing at 3%, do you know what that is in a decimal? You've done this before, but it's been a while.
0.03.
0.03. You move it 2 places, so it's 0.03. Something that is 15% would be 0.15. And think about this. What would something, say, 1.2% be? What would be 1.2%? Because they're not always going to be perfect numbers. Okay,
Wouldn't it be 0.012?
0.012. Okay, good. And if you don't do that correctly, your answer will be way off. All right, this is a pretty good example of things that increase exponentially. So there were 285 cell phone subscribers in Centerville in 1985. The number of subscribers increased 25% per year. Okay, 25% of the original amount every year kept increasing. How many cell phone subscribers were there in 1994?
A lot.
A lot. Well, let's figure out how many. All right, now we got to identify the key things. So Y, well, let's start with the A first. I'll come back to the Y. A is, according to, you go back to the top. A is original amount. What's the original amount in this case? 285. Okay. What is our R? R has to deal with the percent, but we gotta write it as a decimal. What is 25% as a decimal? Now, 2.5, 0.25. Okay, 25%, 0.25. The time will be the number of years between the original amount and what we're looking for. So it's going to go from 1985 to 1994. On will be the time. So it'd be 9. So 9 years. And so Y is going to be the final amount, or in this case, the number of subscribers or number of cell phones in 1994. So number of cell phones in 1994. All right, so what's going to be the equation? Let's plug it in. We don't know Y yet. Zach?
285. Yeah, and then we parentheses 1 plus 0.25.
Okay.
Then an exponent outside, then 9.
Okay, and the only thing I'm going to add is I'm going to put Y equals, just to be consistent. So Y equals 285 times 1 plus 0.25 to the 9th power. Okay, so that is our equation. So how many cell phones were there in 1994? Plug that into your equation or plug that into your calculator. You what? All right, I will go back to there. Write down that equation. Nearest whole number's fine.
2,123.4.
Nearest whole number's fine.
Yeah.
All right, Joe, get that equation down.
Yeah, I'm saying we should round up.
285. Now,
You round down.
hey, listen up. You don't have to, but it doesn't hurt to, you can add these two together. So 285, that 1 plus 0.25 is just 1.25 to the 9th power. So you can do that. And so you do 285, parentheses, 1.25 to the 9th power. Okay, that would be, to the nearest whole number would be fine. So 2,123 cell phones. 2,123 cell phones. So it started at 285 and it went up. And you could use this for, like, if you want to know the year 2000, you just change the time, change the year. Use that same equation. So it's going up 25% per year for that many years. Okay. Now let's take a look at some other things that have growth. Okay. Now is this your next problem you got on there? Okay. So the original value of a painting is $9,000. The value increases by 7% each year. Write an exponential growth function to model this situation, then find the painting's value in 15 years. So 7%, so I would write the equation first, but let's identify 7%. What's that going to be as a decimal? Jalen? 0.07. So it's 0.07. So you're going to get the equation is Y equals the original amount, which is $9,000, times 1 plus 0.07. It says, what's this value going to be in 15 years? Make sure that's a power. So you got $9,000 times 1.07 to the 15th power. Now, once you got that point, or once you're there, now it's just enter it in your calculator. Jay Lee, let me know what you get. Put that in your calculator. Give it to the nearest cent. 0.28?
Yeah.
All right, let me just double check. Not that I don't trust you. Note that 9,000, 1.07 to the 15th power. Yep, 24,800. So in 15 years, it went from $9,000 to 24, almost 25,000. Okay, if it goes 7% per year. Okay. All right, you got a sculpture. So somebody's an art collector here. It's increasing in value at a rate of 8% per year, and its value in 2000 was 1,200. Write an exponential growth function to model the situation and find the value in 2006. So you got y equals a times 1 plus r to the t power, 8%, 0.08. And so it's going to be y equals 1,200 is the original amount. 1 plus 0.08. All right, now what am I going to put in for time? 6 years, because we're going from 2000 to 2006. And so put in 6 years. So every year is growing 8%, and then the new amount is growing 8%, and the new amount is growing 8%. Jalen, what'd you get?
Would it be,
That's a lot of money.
Yeah, something different?
Yeah, I do.
All right, Evan, what do you got?
1,904.25.
All right, Jalen, see what you typed in, and everybody else too. So you got 1,200. Parentheses, I'm gonna make it 1.08 to the 6th power. Yep. So and $1,904.25. So like antique cars grow in value. Typically homes grow in value. Okay, so there's a lot of different things that will grow in value. Now I've seen this type of question a good bit on the OST. Write down that equation. That's what's missing on your paper. Write down that equation. The following equation represents the worth of an ancient manuscript after so many years. Ancient manuscript. Okay.
Yes.
Now hold on, so don't go too far here. What was the original value? Yes, the original value is that number in front. So it was 1,450 for there. Now this next one is where I see the most mistake. What was the percentage of the growth rate, Evan?
35%.
That's the mistake I see. That 3.5%. Okay, because here what you got to do is 0.03, whatever's after the one, move your decimal 2 places. And so it's going to be 3.5%. Okay. If it was 1.2, what would that be? What would that percentage be?
0.012.
You're going the wrong way. Go the other way. If that number is 1.2, so we took 0.05, 0.35 made 3.5, so you want to take 0.2, and actually it would be 20%, because you'd have to move it 2 over. Okay? So think about if I told you it grew 20%, you would say, okay, that's 0.2, and you'd make it 1.2. So we want to be able to go backwards. Okay, with that one. And how many years does this equation represent? 23 years. Now that's all it asks. I don't even know what, does it ask? I don't think I asked you for the final amount, do I? You gotta be able to take that equation and kind of dissect it. All right, flip it over. Things can grow at the same rate. Things can decay at the same rate. Cars lose value after you buy them, unless you have an antique or a classic. But so 95, probably 98% of the cars lose value. Okay, you're not gonna get, like if you paid $10,000 for that used car, or your parents did when you turned 16, 4 years later, it's not gonna be worth more than $10,000. It's gonna lose value. Okay, so that is an example of something that loses value. Now here is that equation. So instead of 1 minus R, or excuse me, instead of 1 plus R, you're gonna subtract that rate. Okay, you're gonna subtract the rate. So if it's 7%, you're gonna subtract 0.07. If it's 2%, you're gonna subtract 0.02. If it's 50%, you're gonna subtract 0.5. Everything else is the same. Okay, everything else is the same. So here would be a case here. Cell phones increase, landlines decrease. Does anybody have a landline in here? Okay, 2, 3.
It's
What's a landline?
What is that?
It's a phone that's hooked to your wall.
That proves your point.
I do know.
Well, yeah, I used to have one.
Like,
A lot of people used to have them.
That was like hip in your day, right?
Well, no, but we didn't have a cell phone when I was in high school. Nobody did. So we had a phone on the wall with a cord on it. So, all right, so Centerville, we're going back to Centerville. There were 17,000 landlines, phone subscribers. The number of subscribers decreased by 12% per year after 1985. Okay, because people were dropping the landlines because they just use their cell phones. How many landline subscribers were in Centerville in 1994? Okay, so Y would be the number of landlines in 1994. A is the original amount. What did we say the original amount was? 17,000. Okay, R, this is the one where I see the most mistakes, 12%. What is that as a decimal? It's 0.12. There's a 0 first, it's gotta be like a number between 1 and 10, like 4% or 5%. The time is 9 years. Okay? Because we're going from 1985 to 1994. Okay. So for any time for percent, and let me just hit this again. 12%, there's a decimal after the 12. You're always going to move it 2 to the left. So that's going to be 0.12. If you have 3.4%, if you move it 2 to the left, it's going to be 0.034.
Can I please use the restroom?
Yes. If you got 60%, what does that look like as a decimal? 0.6. Now here's where a lot of people get confused. If they see 0.6, they're going to say, oh, that's 6%. Or they're going to convert 6% to 0.6. 6% would be 0.06. So you're always moving 2 to the left to go from percent to a decimal. If you have the decimal, you go 2 to the right. Hold on. That should be 0.12 for that one. All right, so now write the equation. So we got Y equals 17,000. 1 minus 0.12 to the 9th power. And actually do this for me because it's going to help you visualize. What is 1 minus 0.12? Use your calculator for that. Okay, Jordan?
88%.
88, so 0.88. So if you see an equation that says 0.88, it means it was a 12% decay because you took 1 minus 12, 0.12. Now type that into your calculator to see how many landlines were in 1994. Christian, what do you got?
5,380.
5,308. Colin, do you agree?
Yes.
Okay. So that was in 1994, so to keep going down 12%. And so like here, we only had like 2 or 3 people in this class at this point that have. Okay, so they've really, obviously they've gone down. Most everybody just uses the cell phone for communication. All right, some other cases where things decline. Okay. Population of a town is decreasing at a rate of 3% per year. In 2000, there were 1,700 people. Write an exponential decay function to model this situation, then find the population in 2012. All right. If you think you know what to do, write down the equation, see what you come up with. If you're not quite sure, wait a minute, and then I'll go through it. Okay.
Probably just round it up.
0. I don't remember.
Yeah, see. Yeah.
Josh, let's get big round.
No,
I got 12 years.
What?
12 years.
Got 12 years.
Yo, how
He's
many
trying to
people,
find the calculator.
how many people are in this town? 12 years.
I'm trying to find 12 years.
A equals what, 1,700?
Yes.
Times 12, your rate, 0.03. Now I like to do the 1 minus 0.03, so 0.97. So when you see that, you got a decay. Joe, what'd you end up with?
1,179.5.
So if we're going to the nearest person, you're gonna round that up. So 1,180. Okay. So you're losing 3% per year. Lose 3% per year each time. Okay, now medicine definitely does the same thing. Sometimes you'll say take every 4 hours. Some medicines will say take every 6 hours. Some will say take every 8 hours. Each medicine's a little bit different from the initial amount to how much your body needs. So they break down at different rates. So in this case here, an adult takes a 400 milligrams of ibuprofen. Each hour, the amount of ibuprofen decreases by about 29%. How much is left after 6 hours? Okay. So you're going to do Y equals the initial amount is 400. Hold on, Tom. You're going to do 1 minus 0.29 to the 6th power. Now, 0.29 simplifies to 0.71. All right, Colin, what'd you get?
I got 51.2 milligrams.
51.2
Yeah, milligrams.
milligrams. Okay, so after 6 hours, it has decreased. Now, once it gets down to a certain level, it becomes ineffective. So, let's say it gets under 10 milligrams in your bloodstream, then it loses effectiveness. So then you're gonna have to, that's when you can take another pill. So like maybe every 8 hours. So it just depends upon the medicine, depends on how fast it breaks down, okay, for that. But that is an exponential decay. All right, the last thing we need to hit is kind of, you probably touched upon this in science a little bit, it's called half-life. Okay,
Not this year.
not this year? Okay.
Oh, yeah.
Half-life is exactly what it sounds like. So something goes from its original amount, like a medicine can have a half-life. So if its half-life is 3 hours, that means in 3 hours, it's half as much as left. Okay. So take a look at that first one, just kind of read through that. Read through that.
Don't be answering.
Now here you gotta watch because the time is a little bit different. The time is the number of half-lives in a given time period. Okay, so it's gonna keep dividing in half. So it's not necessarily the exact time. So if you look at this case here, okay, this element has a half-life of 2 seconds. So it cuts in half every 2 seconds. Find the amount left from a 500-gram sample after 10 seconds. Well, how many half-lives have gone by? 5 of them, because every 2 seconds, you're gonna get a half-life. So T, how many half-lives for this case would be 10 divided by 2, which is 5. So the amount is gonna be 500, 0.5 to the 5th power. Okay, and we can go to the nearest 10th, should be fine. All right, well, since that terminates decimal, we'll put the whole thing, 15.625. Grams. After one half-life, after 2 seconds, how much should be left? Should be, if it started at 500, after 2 seconds, how much should be left? 250, so cut in half. And then 250 would cut to 125. And we start getting into some of the decimals. So it's gonna cut in half every 2 seconds. Now, when they talk about fossils that they find, and they'll say like, oh, that was 4,000 years old, they're using a process that deals with half-life to determine that. It's called carbon-14 dating. But this would be similar. So this has a half-life of 30 years. You have a 100 milligram sample. What would be left after 180 years? Well, after 30 years, you're going to have half of it, which is 50. And then after another 30 years, you're going to have another half, which is 25. But so how many half-lives are there? So it's going to be 180 divided by 30, which is 6. So now our amount equals okay, so it'd be 100 times 0.5 to the 6th power. Go ahead and see what that equals. The terminating decimal, we can write the whole thing, but if it's more than 4 or 5, we'll just round off the nearest 10. Oh, okay, you write that whole thing. is it 1.5625?
Yes,
Yeah.
sir.
All right, is this in grams, milligrams? I got that. Okay,
You're stupid, really.